We are in section 4.4, additional applications of exponential models. You'll notice that there isn't really any notes here. It just jumps right away into examples. And this is because we're going to be applying what we've already discussed in this chapter. So example 1 says, find the x values of all points where the function defined as follows have any relative extrema. And remember, this means mins and maxes. It says classify the x values as relative maximums or relative minimums. So part A says f of x equals 3x e to the x plus 2. And so we need to take a derivative of this in order to find our relative maximum and minimums. And so taking the derivative, we have to use the product rule for the first term, since we have 3x times e to the x. So it's going to be the first part of it times the derivative of e to the x, which is just e to the x, plus the second one, which is e to the x, times the derivative of 3x, or just 3. And then also plus the derivative of 2 is 0. So from here, I'm going to set this equal to 0. I can factor out both a 3 and an e to the x. I'm left over with x plus 1. Setting that equal to 0, I can solve this. Setting each of these factors equal to 0, we have 3 e to the x equals 0 and x plus 1 equals 0. E to the x, remember, never equals 0. There's an asymptote there, so I'm going to go ahead and say that this is never going to be able to be 0. Whereas my second factor is x equals negative 1. And again, looking back at my function, e to the x, the domain was all real numbers. The domain for f of x is all real numbers too. So the domain of our function was all real numbers. So I'm going to go ahead and draw a number line on here. And the only possible place for our critical values is going to be at x equals negative 1. Our derivative is not undefined anywhere. So f prime of x is defined over all real numbers, so we don't have any issues. No place where like the denominator equals 0 or something is undefined. So from here, I'm going to go ahead and put that value on, which is at x equals negative 1. And I'm going to test something smaller than negative 1, I'll test negative 2. Something larger than negative 1, I'll test 0. And substituting in negative 2 into my derivative, which I'll go ahead and circle right here, we are going to get that it is a negative value, so that means that it's decreasing. And then substituting in 0, we do get that this will be positive or increasing. So it goes from decreasing to increasing. So we can see that there is a relative minimum at x equals negative 1. Also noting that it only wanted those x values and not the y values. But if you did need to find that y value, also you need to substitute that x value back into your original f of x function. Part B says f of x equals x squared over ln of x. And again, looking at this, we need to take the derivative in order to figure out where we have those relative extrema. Taking the derivative of this, we need to use the quotient rule. So we're going to have ln of x times the derivative of the numerator, which is 2x, minus the numerator, which is x squared, times the derivative of the bottom, which is going to be 1 over x, all over the denominator squared. From here, we can clean this up a little bit, and we end up with 2x ln of x minus x over ln of x squared. And I'm going to need to set this equal to 0 and solve it in order to find my critical values. And setting this equal to 0, I can multiply both sides by ln of x squared. We get 2x ln of x minus x equals 0. And I can factor out an x. And we have 2 ln of x minus 1 equals 0. And again, we're multiplying here, so we can set each of these factors equal to 0. So we know x is equal to 0, and the other one, we're going to go ahead and solve this. Adding 1 divided by 2, we get ln of x equals 1/2. And then solving this, we can, a few different ways to do this, but ln is log base e of x. And so I'm going to rewrite this in exponential form, which we did earlier this chapter, which is going to be e to the 1/2 is equal to x. So we have e to the 1/2 is equal to x, which is another possible value that we would have for a critical value. And so we have x, thinking about this as a decimal, e to the 0.5 or e to the 1/2 is about 1.65. And our function that we do have a fraction or a rational expression here. And so for this, I know that the denominator cannot be equal to 0. I also know that natural log, you're only able to take natural log of something positive, any logarithm. The domain for any log function is greater than 0. And so for this, our domain of our function is going to be all x such that x is greater than 0. So from here, I can see that x equals 0 cannot be a critical value because this is not in the domain. So the only value that we have right now is 1.65. We do also need to look at the fact when the denominator would equal 0, and ln of x is never going to equal 0. So we know that there's no places where that would be undefined with our derivative. And so from here I'm going to draw my number line, which is not all real numbers, which is actually going to be greater than 0. And I'm going to put e to the 1/2 on here. And underneath it I'm going to write 1.65, which is our approximation as a decimal. I need to test something smaller, so I'm going to go ahead and test 1, and something larger I'll test 2. But again, remember anything in that interval. So testing 1 into our derivative, which I will go ahead and circle up here, you can note that the denominator is always going to be positive. And so looking at that numerator, we're going to have 2 times 1 times ln of 1, which is just 0, minus 1, which is a negative value. So we know that this interval is going to be decreasing. And then looking at when we have 2 and substituting 2 into that derivative, we're going to get that it's a positive value. So this goes from decreasing to increasing. So we have a relative min at x equals e to the 1/2. So the next example that we have, I'm going to go ahead and circle, and we'll look at this one together in class. At the top of the next page, we have exponential growth and exponential decay graphs given. We did discuss this earlier in this chapter, but revisiting this idea. So for both of these, you'll notice that the formula is identical. It's a equals a naught e to the kt. However, the difference here for our growth model is going to be when k is greater than 0, and you can see that k is part of that exponent. And when k is less than 0, we have a decay. And so for both of these, you can see the difference in the graphs being like a mirror image of each other reflected over that y-axis. So the example right below this says Josie is a marketing manager, and she determines that sales of a particular commodity produced by her firm will be declining exponentially once an advertising campaign for the commodity is terminated. Josie finds that the sales level is 21,000 units at the time the advertising ends and 19,000 units 5 weeks later. It does also say to round 2 decimal places. Part A says find S naught and K so that S of T equals S naught e to negative KT, gives the sales level T weeks after the advertising campaign has ended. What sales level should Josie expect 8 weeks after the advertising has ended? And so the first thing is, given what we have up above, it says Josie finds the sale level is 21,000 units at the time the advertising ends. So that's we'll call that times 0. So I'm going to call that S of times 0 equals, and 21,000, and I'm going to go ahead and say just 21. And so this is when T equals 0. So 0 time after that advertising has ended. Then it says we also know 5 weeks later, and we are dealing with weeks here, so I'm going to say S of 5 is equal to 19,000 or just 19, which we are also given. And so this is when T is equal to 5. And these are listed, both of them, in thousands. You can definitely still put on those zeros. That just makes it a little bit more bigger numbers to be dealing with, so sometimes more errors will happen. And so from here we have a formula that they gave us, which was S of t equals S naught e to the negative kt. And so I'm going to go ahead and substitute in 0 because we were given that information. So when time is 0, we have S naught e to the negative k times 0. So working this out, we have e to the 0, which is just 1, and so we know that S naught is equal to S of 0, which was 21,000. We should know that. Hopefully that makes sense. But now we know that S naught is 21, so our function is now S of t equals 21 e to the negative kt. So we found S naught, which is part of this. So go ahead and circle that. And so from here we know S of 5 is equal to, and I know my equation is 21e to the negative kt, so k and then t is 5 in this case. And so from here I know S of 5 is 19,000, or 19 in our case, e to negative 5k. From here I'm going to divide both sides by 21. So we get 19 over 21 equals e to negative 5k. And again, to solve for an exponent that we do not know, we need to use a logarithmic function, and I'm going to use ln. So I'm going to go ahead and take the natural log on both sides of our equation. So from here we have ln of 19 over 21 equals, and our right side is going to simplify to just negative 5k from our exponential properties that we had earlier in this chapter. Solving for k, I'm going to divide both sides by negative 5. So we get k equals ln of 19 over 21 divided by negative 5. And substituting this into our calculator, we're going to get that k is approximately equal to 0.02. And so now, since we know k, our function is now going to be S of t equals 21e to the negative 0.02t. And it's asking for us to figure out what sales levels should be expected after 8 weeks once the advertising has ended. So I'm going to go ahead and find when t is 8. So S of 8 is equal to 21e to the negative 0.02 times 8. And so substituting this into my calculator, we get 17.90. And again, remember that we were dealing with thousands of units. So I'm going to say 1,000 units. And so you can either leave it like this or just say equivalently 17,900 units. Part B says, at what rate, remember rates are derivatives, should Josie expect sales to be changing t weeks after the advertising ends? What is the percentage rate change? So first thing is that rate we need is a derivative. So taking the derivative of our function, and again our function I will rewrite is S of t equals 21e to the negative 0.02t. And taking the derivative of this, we're going to have 21e to the negative 0.02t times the derivative of that exponent, and the derivative of the exponent or that inside function is just going to be negative 0.02. And so working this out, we get negative 0.42 e to the negative 0.02t. So do note that this is the rate that Josie can expect sales to be changing t weeks after. So if she wanted to figure out, like we did in part A, 8 weeks after, we could figure out that rate that it's changing 10 weeks after, 14 weeks after to give her an idea. So it also asks for what is the percentage rate of change. And we saw this earlier, but the percentage rate of change is going to be equal to that derivative divided by the function times 100 to make it a percent. And so our derivative function and our function we have both listed, and so I'm going to go ahead and substitute this all in. Our derivative was negative 0.42 e to negative 0.02t all over s of t, which is 21 e to negative 0.02t times 100. And so you can simplify this before you even substitute anything into your calculator. You'll notice that e to the negative 0.02t is in the numerator and denominator and will reduce out. So working this out, we do get negative 2. And so again, this is a percent. And so what this means is that sales are declining. And it's declining because it is negative. So at a rate of 2%. And again, we're dealing with weeks, so per week. The next thing that we have says, suppose you own an asset whose value increases with time. The longer you hold the asset, the more it will be worth. But there may come a time when you could do better by selling the asset and reinvesting the proceeds. Economists determine the optimal holding time for selling by maximizing the present value of an asset in relationship to the prevailing rate of interest, compounded continuously. And so we have an example at the top of the next page that I'm going to go ahead and circle, and we're going to look at that one also together in class. Below this, it does say logistics curves. And this is an approximately exponential at first function, but it has a reduced rate of growth as output approaches the model's upper bound called the carrying capacity. And it says for constants A, B, and C, the logistics growth of a population over time x is represented by the model. And so we have the model f of x equals, and this is c over 1 plus a e to the negative bx. And you can notice a couple things on our graph that we have. One is going to be the carrying capacity as stated up above. And so this works a lot of times for models. And so when you're modeling a pandemic or an endemic or the flu, anything like that, or populations growing, there's a carrying capacity. So it doesn't go on forever. We're going to hit a maximum amount that we have, and that carrying capacity is C. You can see that the function that we have here, the logistics curve that's given, has a few interesting points labeled on it. One is going to be the initial value of the population, and this is going to be when our x value is 0, or time is 0 for that population curve. And then we also have the point of maximum growth. And you can see that that is listed on there. And we have a formula also for that. So the x value is ln of a over b, and the y value is c divided by 2. So a few things to note on here for our logistics curve. The example at the top of the next page says public health records indicate that T weeks after the outbreak of a certain strain of influenza, approximately Q of T, which is equal to 20 over 1 plus 19e to the negative 1.2t thousand people has caught the disease. And this is also in thousands of people, and we are dealing with weeks. So things to note on here. It says round 3 decimal places. Part A says how many people had the disease when it broke out. It says how many people had it 2 weeks later. So when it broke out, our weeks would be T is equal to 0, and 2 weeks later would be T is equal to 2. So we need to find the number of people, so Q of when time is 0, and also when time is 2. So when time is 0, substituting in 0, we get 20 over 1 plus 19e to the negative 1.2 times 0. And working this out, we get e to the 0, which is just 1. And so let me just simplify to 20 over 1 plus 19, or 20 over 20, which is 1. But remember that we're dealing with thousands of people. So you can also write this as 1,000 people. So they are the ones that had the disease initially before it broke out. Q of 2 weeks later, this is going to be 20 over 1 plus 19e to negative 1.2 times 2. And so from here, I'm going to substitute this in on my calculator. I'm going to simplify it just a tad. And we get e to the negative 2.4. And I can substitute that into my calculator. And working this out, I get 7.343 thousand people. And so you can see that this is a big change, and quickly. So in 2 weeks, it went from 1,000 people to 7,343 people. Part B says, at what time, in weeks, does the rate of infection begin to decline? And so that's at that inflection point. And so looking back at the graph that we had on the previous page, the point of maximum growth. And so our time, our t value is going to be at ln of a over b. And so I'm going to go ahead and write that down. So t is equal to ln of a over b, as stated up above. And our a value that we have is 19, and our b value that we have is 1.2. So we have ln of 19 over 1.2. Also note that that negative symbol is not included with the b. So dividing this on your calculator and rounding 3 decimal places, this is approximately 2.454 weeks after it broke out. Part C says, if the trend continues, approximately how many people will eventually catch the disease? And so this is going to be at the carrying capacity. And so for this, if you look back at your graph, that carrying capacity was at y equals c, and our value of c is 20. And since we're dealing with people for this, people are in thousands of people, so we'll say 20,000 people. And so I'm going to go ahead and put my zeros in and say 20,000 people.